Hi, my name is Aris. I just wanted to start off by, hi Gabe, by thanking like my mentor, my research manager, and like everyone who operationally made it possible for ERA to happen. Yeah, had a great time and really appreciate it. So throughout ERA, I have been working on understanding advancements and regulation for semiconductor chip design software. So what does that mean? I was basically interested in the question, how might we expect semiconductor chip design to be affected by AI? So I have a simplified version of the semiconductor supply chain up there. Basically, you design a semiconductor chip, you manufacture it, and then it can go out and, I'm interested in AI, so it can go out and be used to train and deploy AI systems. So one question that came up for me when thinking about how software might interact with hardware supply chains was how much might we worry about software contributing to something like an intelligence explosion? And so an intelligence explosion might be when you have like an AI system that suddenly gains a lot of capabilities very fast and kind of like explodes in the amount of capabilities it gains. And the reason I was maybe worried about this is if you have an AI designing chips, it could lead to more efficient AIs being trained, which could maybe lead to more efficient AIs designing chips. And like possibly this iterative process could lead to an intelligence explosion, is something I was worried about. And I broke this question down a bit more into trying to figure out how much can you improve current chips that we use to train AIs? And how much do we expect that you can improve? How fast do we expect that you can improve current chips? Another question that came up was basically thinking about like, so it's kind of hard to regulate software in a way that it's not necessarily to regulate physical things, because software can be diffused in these like weird ways. You can like download it, you can open source it, you can leak it. So the West currently just like absolutely dominates the chip design market. What would happen if we created like a chip design AI and this were no longer the case? So those are the main two questions I've been exploring. On the first one, thinking a bit more about could a chip design AI lead to an intelligence explosion, my current claim is that and I'm sorry, the answer will be maybe toward the end of the claim. I think we'll likely see a 2 times to 20 times performance gain from AI in chip design before we have a like generalized scientist AI. And I expect that larger performance gains might be possible after there's like a super intelligent AI that exists, but maybe not before. Take this claim like held pretty weakly. I think I like change my mind on this like every few days, like exactly what the parameters are. But basically the reasons why I believe this currently are with an AI capable of doing human level labor, I've gotten consistent replies from people in hardware who I've interviewed that they think that within the first year you could see a 2 times performance gain increase from just having AI that can automate the same type of labor that engineers do. Not having like a super intelligent AI or something like that. So again, this is just like an AI who could narrowly do that task. Another reason why I'm not as worried about intelligence explosions is I think that there are pretty long cycles for feedback loops with hardware that you don't have like as long of cycles with software. Specifically, I think if there's a concerted effort for a bunch of the leaders in AI to try to make new chips as fast as they could, it would still take them maybe like 6 to 9 months to actually design, manufacture, and start training and deploying AI systems with these chips. I also have found that there's a sense among hardware researchers that if you want like really insane intelligence explosion levels of capabilities, you would probably need something like a super intelligent AI to help you get there. But there's a lot of uncertainty over like what these capabilities might be and like how capable chips could theoretically become. So I started off by basing my investigations around these claims from a chip hardware engineer. He thought that there would be at least a 1 times performance doubling if we had AI developing, doing like the full development of semiconductor chip design. And this is roughly equivalent to about 2 years of typical hardware efficiency improvements. He thought that there was possibly, instead of a 1 times doubling, a 5 to 10 times performance gain in the first year that this is developed. This would depend on like how much the AI could do like kind of basic research things in addition to just only doing the actual engineer's job. And that would be roughly equivalent to 4 to 9 years of typical hardware efficiency improvements. I spoke with a few other people, and they estimated that within 1 year, they came up with the same estimate of about 2 times efficiency gains. And there is a bit about their considerations on the side. But then I also was trying to get a better sense of like, what are the potential all-time performance gains we could get? Like, how capable could these chips be? How much could they influence AI development? People's answers varied a bit more here. So we see generally the median answer each person gave in their like confidence interval was about 10 times, 100 times, 20 times. So this is how much more efficient chips could be than they are currently. But there is a lot of uncertainty here. You can see one confidence interval ranges from 10 times to 10 million times. And this is generally based on the idea that like, well, if the AI was like really super intelligent, if it could control a lot of the parts of like designing chips, of like of changing the other parts of like manufacturing and optimizing a lot, maybe we could see like insane chip quality gains. So thank you. What does this mean? Generally, I think this means that looking at chip development is going to be relatively predictable compared to other parts of AI development. And I think that this means that researchers and policymakers could foresee most hardware capabilities gains, or at least they could mostly foresee these gains compared to software capabilities gains. And I think that's like pretty useful for designing policy. And then the second question was something more like, what would it mean to regulate an advanced chip designer AI? And I turned that question into something I could look a bit more into, which was, how well do current regulations on China for chip design software work? And so a bit of jargon before we get into it. EDA is electronic design automation software. It's a set of software tools that are essential for designing semiconductor chips. A node describes the features of a semiconductor chip. It's measured in nanometers, and the smaller the node, the better. And GAFET is a particular type of technology that is used when you're designing small chips. And by small chips, I mean like small nodes. Side note, it's also like insanely expensive and insanely technologically advanced to design something like a 3 nanometer node. Like just think about nanometers. That is like the size we are dealing with like fabrication. It's pretty insane. Great, so EDA, node, and GAFET. GAFET, just think of like really advanced nodes. So basically these are current estimations that I have on Chinese capabilities for fabrication and access to EDA. So by fabrication, I mean like, can you make the chip? By EDA, I mean, can you design the chip? And ignore that like blank row there. That was just a mistake. But basically, at this point, my current understanding is that China could domestically fabricate chips that are over 14 nanometers, and theoretically, they could go to foreign fabrication companies to get chips that are 3 nanometers and larger if they follow certain requirements. Unfortunately, things are like a bit muddy here, but you can just generally take that for now. And Chinese chip designers would need to pirate or pay for EDA for nodes greater than 3 nanometers through 28 nanometers. So these are basically identifying the places where they don't have strong domestic infrastructure and may be reliant on the US. And so how well, you can see here, some of these things are like Chinese domestic capabilities, other things are regulations on China. So how well do our regulations currently work? For EDA, they seem to probably be working pretty well on individual Chinese pirates. There are like some technical difficulties with pirating 28 nanometer and lower EDA. As EDA becomes more advanced, it becomes harder to hack. And maybe these regulations work well on corporate piracy. So there's some analysts who think that past EDA restrictions have been really successful. In particular, they've like removed top Chinese chip leaders from like the top 5 of their markets. And also, it should just kind of be obvious if there's piracy from a Chinese firm trying to fabricate chips that are like way too advanced for anything that they could make at home. So if you see someone being like, hey, here's my 3 nanometer chip, can you make it? It's probably likely that they're pirating it because they just can't make this technology. But maybe these regulations don't actually work very well on corporate piracy. Some reason we have to think that is that EDA companies have been rumored to just like create shell corporations to sell things and keep their markets in China with deniability. And the bureau that is supposed to be regulating this is poorly funded. So how could we improve policy? Potentially, we could sell EDA over the cloud. We can encourage EDA makers to create custom export control friendly EDA for overseas customers, increase funding to regulators, improve screening for piracy at the foundry and customer auditing, and plausibly we could have the anti-piracy tactics that make anti-piracy below 28 nanometer EDA effective. Oh no. Classic. Plausibly, we could use those to inspire future software export controls or frontier model controls. And now it's Q&A. And I have possible suggested questions you can ask me that just like I could clarify things about. But yeah.